Hi everyone, welcome to Lab 5, Magnetic Braking with Faraday. The purpose of this experiment was to collect data on a magnet falling through an aluminum tube and then observe and apply Faraday's law. Some key fundamentals for this lab would be Faraday's law, Biot-Savart law, Newton's second and third law, Ohm's law, magnetic force in a loop, and the time derivative of magnetic flux of a dipole, and then all of the equations are listed. And then my results from the experiment for my computational time was 1.12 seconds, and then for my experimental time was 1.25 seconds. In this experiment, the magnet models a magnetic dipole, and then the aluminum foil models the tube that it fell through. Some key assumptions: air resistance is negligible, and then that the force of gravity and the magnetic force are the only forces acting on the magnet. For the experimental procedure, I defined the system to be the aluminum tube and a magnet, and the surroundings to be everything else in the room. For the procedure, I use a magnetometer app to mark the north and south pole on the magnet. Then I set up my camera to record and I dropped the magnet through the aluminum tube. Then I calculated the amount of time it took for it to fall through the tube. And I repeated this like 5 times and then averaged the times that it took. So here are all the measurements and data I collected from the experiment. The length of the tube was zero point 0.3 meters, the width 0.006 meters, the inner radius was 0.024 meters, and then the radius was 0.03 meters. Mu was 2.21, and then the magnet mass was 0.025 kilograms, and then the average time that I calculated from the 5 trials was 1.25 seconds. So here's my code from GlowScript. I began by initializing the constants, then I created the aluminum tube and the bar magnet, as you can see here. And then after that, I defined the function for the magnetic field due to the dipole and the function for the magnetic flux created by the bar magnet. And then I calculated the gravitational force on the magnet and the magnetic flux on the ring as a result of the falling magnet, as you can see here. And then from there, I calculated the current through the aluminum tube. And then in steps 5 and 6, I calculated magnetic force of the falling magnet on the tube, as well as that of the magnetic tube on the magnet. And then finally, I calculated the net force, which was used to calculate the changing velocity and position of the bar magnet. And then you can see the program run here. Here's a closer look at the velocity versus time graph. You can see like how at first it increases dramatically. That's like the force of gravity and the magnetic force being unbalanced, and then it evens out once they become constant. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise, and how can you know? Blue is clockwise, red is counterclockwise, and I know using Lenz's law. What happens to the dynamics of the system when you flip the magnet around? So it changes the direction of the current, but everything else stays the same. The magnet still falls through the tube relatively slowly. How does the total time in tube of your real world system compare to that of your computational system? How might the computational system be made more accurate? The two models are relatively close, but it could have been made more accurate by splitting the tube into more rings. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So, the gravitational and magnetic forces are imbalanced when the velocity changes, but they are balanced when the velocity remains constant. Now for the discussion. There are no model discrepancies. The only sources of error would be the incorrect value of mu that was calculated from lab 3, or human error when measuring the time for the magnet to fall through the tube. And then for what if questions, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Due to Ohm's law, the induced current would increase dramatically and the magnetic force would increase dramatically. This could possibly counteract the gravitational force, which would keep the magnet from falling. Question 2 says, what if holes or slots were cut into the tube? How would this affect the ring's current in your model? So the induced current would decrease dramatically because the cuts would disrupt the current, and the magnet would fall through much faster. In conclusion, from this lab, I gathered a deeper understanding of Faraday's law and its real-world applications, and a better understanding of induced current and EMF resulting from changing magnetic flux. Thank you for watching, and that is the end of Lab 5 Magnetic Braking with Faraday.